Okay, good afternoon, everyone. Is it a good afternoon? Yes? I'm Eckhard Groll. I'm the head of the School of Mechanical Engineering, and it's my distinct pleasure to welcome all of you to today's Purdue Engineering Distinguished Lecture Seminar. And I have the great honor to introduce our Dean of the College of Engineering, who is then does the introduction of our distinguished speaker today. The Dean is Professor Arvind Raman, and Arvind is a faculty member in the School of Mechanical Engineering, even though his appointment in ME currently is 0%. Right, so he's 100% Dean, but we still claim him. We still love to have him. And with that, he certainly leads the college to the most consequential college, right, by 2030 in the nation. And it's an ambitious goal, but we're all working very hard to get there. And so with that, I would like to welcome Professor Raman to the stage. Thank you.
Thank you. Thank you, Eckhard. Good afternoon, everyone, and welcome to this 8th and actually final Purdue Engineering Distinguished Lecture in this 2024-2025 academic year. I'd like to welcome all those who are here in person and all those who are watching this event streamed live as well. It's an honor for me today to introduce our distinguished lecturer, Jian Cao, who is the Cardus Collins Professor of Mechanical Engineering and Materials Engineering at Northwestern University, where she concurrently serves also as the founding director of the Northwestern Initiative on Manufacturing Systems and Innovation, Manufacturing Science and Innovation, as well as the Associate Vice President for Research. I don't know how she does all of this, but it's pretty impressive. Dr. Cao is a world-renowned authority on manufacturing systems and processes, in particular deformation-based manufacturing and laser additive manufacturing. And the impact of her work has been tremendous, and she's been recognized in so many ways for it. She's a member of the National Academy of Engineering. She's a member of the American Academy of Arts and Sciences as well. And she's the recipient of many prestigious awards. Among them, the Society for Manufacturing Engineers Gold Medal, among them the DoD Vannevar Bush Faculty Fellowship, among them the ASME Ted Belichko Applied Mechanics Award, and the list goes long and long. It's really long, the list of recognitions she's received. But I'd like to point out that Dr. Cao has also been very active. She's been very active in national service by serving on many national and regional boards. She serves on the board of the National Academies for Materials and Manufacturing and on the Academy's Standing Committee on Defense Materials Manufacturing and Infrastructure as well. She serves on the board of the Society for Manufacturing Engineers, and regionally, locally, she serves on the board of MHub, which is a hard tech and manufacturing startup incubator in the city of Chicago. So without further ado, please join me in welcoming Dr. Cao to the stage.
Well, it is my great pleasure to be here, and thank you so much for the warm welcome. So one thing that I would say is, particularly with the manufacturing, I always say it's manufacturing is an integration platform, and it requires so much different talents, specialties coming together to make it happen. Therefore, I was very fortunate to work with friends, colleagues, both inside and outside of Northwestern, including colleagues here at Purdue. So it's my fortune to be in this area. And so I very much appreciate this opportunity to here and talk to you. Do you hear echo? Okay. This is very flexible. Great, that's my topic. Flexible manufacturing processes. So I would like to share some of the recent ones that has been going on in my lab, as well as my collaborators on various different projects. And particularly, I'm focusing on the physics-based AI-assisted design, the control of manufacturing processes. I was here about 2 years ago, give the mechanical engineering seminar, and I will promise you there will be only 5 slides overlapping with the previous one. So with that, I would first acknowledge the student and postdocs, as well as our manufacturing group, and Northwestern. Without them, we just couldn't do anything. So in terms of the goal, when we're thinking about the automated goal for, engineering particularly, as well as business, right? When you're thinking about how do we make an impact in the various different aspects, one of the things interesting will be to have this autonomous process from design to manufacturing. And start with I could be a little bit biased, my domain as an undergraduate student. How many here are undergrads? 1, 2, good. So undergraduate education, very important. So it was materials engineering. And so we start with when you look at the material science, you're looking at the structure and how the process influence and what's the property going with. So starting with the material that you're working with, and then, we add machines, right? This is where the control start to come in, sensing start to come in. That was my second major as an undergrad as a control. And then in order to make this happen, we love to, build our own machines, open architecture, so we understand what's under the hood, we call it. And then the part of this is, as I mentioned, the design. The design that I'm focusing on is more and more about co-design of the product materials and manufacturing process together, because the potential of that is just enormous. And the other thing interesting is also because of the parameters of design freedom that you have is increasing tremendously when you have all these 3 things coming together, right? And in order to do this well, you really need mechanics. So this is where the graduate studies start to come in. So my graduate training was in mechanics as well as control. So when you put all these things together, the qualification, certification of the parts start to come in. And these days, then we are also talking about the simulation and data connected with all of them. Certainly AI is a very hot topic. And then you can think about how AI is going to help with the different processes. And to me, because of the lots of knowledge accumulated, as well as the freedom to jump from one to the other, if fundamentally is the same, that's why physics-based is so important, right? And so one of the things that we are focusing on particularly is flexible manufacturing processes. So when we talk about flexible manufacturing processes, the volume could be not so much, but it's very much linked into the distributed manufacturing or point of need manufacturing. So one of the things that we did with Ohio State as a lead is this ERC HAMR, hybrid autonomous manufacturing, moving from evolution to revolution. So the vision is if you have a flexible processes, a cell, you can do additive, you can do machining, you can do deformation. And the goal is certainly to get the property as well as the geometry right? The performance of this. You can have it on a ship near the hospital, in space, particularly here, we are talking about space manufacturing a lot. So in space as well as around the corner. So the vision is if you could have this coming together and what would be needed. So as you could imagine, the design freedom, it's not just about point kind of one-shot design. It's very much time dependent as well as localized material dependent. So spatial and temporal degree of freedom. So to me, so in our lab, we have been doing sheet metals for quite some time. And the low volume applications of space, you can also see in the space when the sheet metal parts, which has advantage in terms of the temperature tolerance, right? But in addition to this, there are lots of also potential in the new ones. For example, this is a Google building with a sheet metal as a roof, right? And this process made it is the so-called incremental forming process. So the incremental forming process we do is so-called double-sided incremental forming. Instead of doing dies, which you probably need a lot, very long time, like 5 to maybe even months to get to the die, and then you make the part. With this flexible processes, you can really make all these different geometries from a single machine, but computer-wise, software-wise, controlled very differently. So this was like, if you look at the reference, but that was back to 2008, we started this, and really glad to see that companies are picking up. So the next video is actually from a startup company, but now with over 100 people already in LA, and the company is called Makino Lab, and they have been scaling this one up with the more degree of freedom added to it. So the sound should come out if you could. Yeah, but if it doesn't come out, yeah, I'm going to stop the video right here. But the message is, when you have robots combined with this flexible processes, yeah, you can actually do quite a lot. For example, if you look at all these 4 different parts, and with different materials, you can do it within a week. And that is the speed up we are talking about in terms of the flexible processes. However, the challenge of this is that when you do this, if it's a simple geometry, it's okay. But if you have more complex geometry, how do you make the first part right? And so a lot of mechanics and control goes into this. You need to understand the material behavior and plan out the 2-pass and do an active, 2-pass feedback control. The bottom line of this is actually predicting the force that's needed during the forming, because we know that the force, transfer to stress in the materials, and when you do elastic, unloaded, you have lots of spring back. And therefore, the force control, the force prediction is critical. And so the question that we ask ourselves is, when we do in my lab, right? So here's a scale, Northwestern ones. Here's a human In my lab, we have very small parts because we don't have lots of space. And you see the Makino lab, it's here, 1.5 meter by 2, could be up to. So how do we get the knowledge from what we have in the lab, combine with theirs, and translate it to, different scale, right? So our goal is, can we have the prediction, which could be machine size independent, and when you have a different actuations, you also going to have different rigidity in the system. Then the system setup, the tool setup, can you be agnostic of that? Certainly, if you change the material, change the geometry, can you be agnostic about this, right? So how do we do this? So AI comes as a helpful thing. What we have is here's a schematic. And what we have is, when you think about the mechanics of this, the initial several round of the forming actually has already material. If you look at the force data, the initial one, it quickly goes through from the elastic to plastic. And for this area, you kind of have already the integrated machine rigidity, material properties, right? It's kind of embedded information already. And when you do the first few rounds, these are forming of those bottom lines. So they are not to the final geometry yet. So if you could learn from the initial points and then adapt it to have to have this information, and then you can use that to predict what's going to happen later on. And that's our approach. And in order to get to this geometric agnostic, we also use a GN in the middle as an architecture for the model. So the bottom line, what I'm trying to say is, understanding the fundamental mechanics of the process actually helps you to design the strategy about how you want to use machine learning, AI in the prediction, right? So we did this, and we can see that you actually pretty nicely predicted, and we are actually continue working on this to get more. So the other process that we do in the lab is laser additive, particularly with the metals. And as you can see, that's another flexible manufacturing processes, right? And here we have two different systems. On the left is powder blown processes. So here the powder blown, and then the direct energy deposition. We also have multiple lasers, including blue laser. And here what we did, we really we built up this machine ourselves. As I mentioned, the other circle that we have is we really want to understand and the process. So we build up our system ourselves, and there's a metrology system we add on, as well as multi-helpers and different sensing mechanisms. So this is DED. And I believe last time when I was here, we talked quite a lot about DED. So this time I'm not going to talk too much about this, and I'm going to actually focus more on the PBF, laser powder bed. And from the laser powder bed ones, I'm pretty sure people know how this works. And the way that we do it, we got a donation, we tear off the sheet metal panels, and then we manipulate the lasers, instrumentations on this as well. So for doing this, you're going to see later why we want to do this. But let's talk about this process, laser powder bed process. And here, a common practice when you have a new material is you build a lot of those blocks, try to find out what is the right process parameter to give you less porosities and the more dense. However, if you transfer to something else, it really doesn't just transfer easily like this, right? And so one thing is, this is very well known, and widely used by the community. If you look at the laser power versus the velocity, in the middle, these are the good process window. And on the far right, you can see lack of fusion. On the left top, you have keyholes, and then you have bottling, situations. So you try to avoid that and stay in the middle. So we work with the DMG Mori and also Zeiss on this, and they design this very interesting features, which you have bulk material in the, at the bottom, and then you have different cylinder size, different fins and the different kind of, angles. And when they process this, they say, okay, I'm going to process this part and using different combination of the laser power and the velocity. So they did that. When they did this, and then after that, they CT scan it. So you can see the reds are the porosities. Many times, basically, we are saying it's not good. The greens are good. As you can see, certain process parameter gives you lots of red, right? And they are in the middle, which is good. However, if you do a little bit more careful analysis, which is this one, and here, if you go with they have 8 pairs, power, velocity. So for every the same position, basically it's the same process parameter. What's different, each block here is everything is counted the same, just counted all together. These are the porosities. If you just count the body here, the yellow ones, and these are the porosities. If you count the fin 1, fin 2, blah, 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 and each one you basically look at what is the porosity volume. What you can see is that, this one, for example, it's very nice, the green one for this little thing, but it's very bad for the body, right? So the question is, basically this illustrates the same process condition, really depends on your geometry and where you are. It will change the results quite dramatically. Now the question is, how do we do such that when we design the process parameter that we can make it everything green? So to understand this, we started with our experiments at Argonne National Lab. We use the APS, the X-ray, so you penetrate that, you do the laser, you have a powder right here, and then you come with the laser to melt it, right? And then basically do the single scan. And here, one thing is because of the power of the X-ray here, for material-wise, it's about 400 micron thick, okay? Therefore, it's really localized ones. But we can learn a lot from this. And the idea of this is that I want to have the ground truth, and then we have this sensor array, which is a photodiode system. We put them together because this system you can install on traditional or commercial machines, right? So if we can have a good correlation between the ground truths that we know learned from APS and with the photodiode system, then we can transfer this knowledge to very large parts in different areas. So with that intention, we went to APS, and then you can see here, as the laser go from right to left here, you see the mel pool over here. This is a raw image, and then after you go, you can see actually sometimes they leave the keyholes. They leave a porosity right there. So it's very hard to see, right? So you process it, and the processing ones. What I want to give you the attention is the top row and the bottom row. The bottom row, particularly the blue ones. The blue ones are the melt-pool depth. And so one of the way you have the porosity is this keyhole, it's not stable, and then it collapses, and therefore, it entraps the vacuum or and therefore create this, this porosity. So what we see is it's a really good correlation between this called TAD signal, which is the integration of these, energy intensity. And then the peak of this really corresponding to really well about this melt-pool depth collapse. And actually the percentage for this one is 92%. So what this tells us is if we can sense this from the real process, we kind of can assume that maybe a keyhole is likely to be formed, 92% to be formed, right? So with that, the idea is, can we use this to look at larger scale, right? As well as how do you design the process to overcome this porosity issue. So we use this method, and there are some additional data processing methods that I'm not going to have time to talk about. But you can see that when we did this, using those peaks, and this is a part made on the commercial machine, right, the DMG Mori that we had, the one that we strip out a lot of metal and install the photodiode system. So we count the TAD peak, versus after, as I mentioned to you, with the 8 different sets of the parameter, they have the pore count. And you can see that it's a really great, correlation. The one that's outlier right here is because this one, the process parameter of this one is lack of fusion, not due to the keyhole. So this gives us some confidence, and then we are saying, okay, can we look at the different geometries, Can we make the process reduce the porosity? So the idea is the following. You have the CAD file come in, and then you certainly have the scanning path designed, so you can output these 2 paths. And then what we do is called a mechanistic feature, which I'm going to tell you a little bit later. And those features, we use those features and using the machine learning tool to predict what is the temperature distribution that we are going to see. And if we see the temperature distribution is actually a signal of those peaks as well. And so if we see that, then there's additional peaks. Then what we are going to do is we are going to lower the laser power and adjust the laser power accordingly, locally, right? And then using our, Gamma is an internal code that we developed, and then change the laser power, and then we implement to the real parts, do another build by having this laser power not consistently, but change as we go, But this one, you can see that this is each layer, how we are changing the laser power. And one thing that, as you know, the qualification certification is pretty hard for AM. We hope with this one, because it's an open loop control, and we know the machine, we know what's the laser power that we are giving, and gives a little bit easy time for the part to be qualified, right? So the key thing is, first, we need to be able to predict what's going to happen, as I mentioned, right? In terms of this is, the high temperatures, potentially you're going to give those peaks. So this is measured with the photodiode system, and here is the predicted ones using the mechanistic feature that I mentioned to you earlier, and that I'm going to show in details later, to predict what's going to happen. Now, one thing that I want to caught your attention is this one. So here, for example, around the boundary, your laser is turning, okay? So you're turning the laser, and then you see the temperature profile. But also here in the middle, the laser is also turning, right? But the intensity is very different from the edge. But basically, this tells us, you really need to take into account the material geometries, part geometry, in addition to just the two paths. So this gives us, this idea about the features that we need for predicting the profile, right? So certainly you have the laser scanning speed, the power, and this SD is what I mentioned to you earlier. So when you think about this, the temperature is very much depends on material thermal conductivity and many other things. So if you have a solid part versus if you have powder part, you are going to see different behavior, right? So the way that we characterize, try to be agnostic to geometry is to develop this feature. We use, you can think about this as a hemispherical region. And if it's a solid, if it's 100% solid, it's 1. If it's partially solid, you can calculate the percentage. You have multiple about these rings, actually multiple of these hemispheres. And then by doing that, it's a vector, right? And here you have vector of this SD, which kind of gives you an idea what is the solid area surrounding this point. Similarly, as I mentioned, the edge versus the middle is also different. So you can also get in the edge features by doing this geometric analysis. Everything like this, the features, you can do it offline. So once you have the part, you can analyze this, right? And therefore, you have this magnetic features, and then we use the training, train on a couple of those runs, and then you can use that for prediction. So here's the result. And on the left is something that we did with the nominal average, everything is uniform, and you build it up, and you see the porosity. Now, one thing that I want to say is for this exercise, we use the best known parameters. So this is not comparing to like some of these bars you see it's really red. We are taking the best parameters that you get from the constant processes, and then compare. So this is the one on the right, which you call controlled. And you can see, obviously the porosity is much less, as well as the shape, of these are much more uniform. And this is particularly important because when you look at the fatigue analysis and the impact of this, right, you can actually have a significant impact there. So we talk about, the machine that we modify this, we added the sensing in. We talk about for the qualification certification, how we do the laser control to give you better parts. And so the next thing is also this PSPP. We know the property-wise is very much depend on also the thermal history, right? And therefore, when we build up the parts, we want to know what's the thermal history that it's experiencing. And the particular work that we are doing here is we want to also check the effect of the neighborhood part. This particular, for example, here, if we are just interested in these regions, because when you try to build AM, you try to stuck as many parts of there as possible, right? Because the build time is pretty much, dominated by number of the layers. So if you do that, you have, certainly people put lots of tensile specimen and the other things. Our question is how the surrounding areas will actually affect the parts, depends on where you are. So one thing that, just a quick illustration, if you look at the group of them in the middle, if you do consider the surrounding parts contribution, you actually have this kind of thermal image, you can just at one moment. If you just simulated the single build, and you can see it's going to be very different compared the case when you have the surrounding ones. The challenge of considering surrounding ones is the computational time. So what we are saying is, is there any way to quickly capture that? So the idea is pretty simple. It's like, we know the temperature obviously depends on the heat flux coming in. So can we actually, instead of modeling the laser path, path-wise, can we create an equivalent heat flux model? And because after each layer you cool down, so the idea is if you do this, layer by layer scanning path-wise, but if we just do the heat flux equivalent ones, after a certain time, they become equivalent. So we take this equivalent ones, and then so we square, you can do square, you can do the circular cross-section. It's almost like the UniCell model, right? And then you put those one in, and we can simulate, for example, this one as we build up for the entire plate. So the first animation that you see is using this one. Now, very quickly, if you look at, I mentioned about these photodiode system. So basically, this is a sanity check, not quantitatively, but qualitatively. If you have multiple parts that simulate at the same time, the orange line is our experiment using the photodiode. And the blue line is a simulation. So you can see that in general, qualitatively, they work much closer compared to just a single part. So this gives you a very quick way of checking your temperature profile. So finally, I want to talk something about the design. Design, as I mentioned, is not just, particularly for this one, I'm looking at the process design. So last time, 2 years ago, I talked about how we designed the laser power with the DED system. And the goal at that time is we want to have certain thermal history. And then in order to do thermal history, we know the heat will build up during the DED build. So what we developed was a differentiable gamma simulation code for this DED, and then we can approximate laser power with a neural network. So basically, this is a PDE, PD coming together. You can do optimization at the same time to calculate what's a laser power that gives you the desired thermal history, right? So this was on the build. And the question is now, as I mentioned, I'm coming back to the forming. Can we also do it for forming? And the package that we develop is this called JAX FEM. So this one is a differentiable. We are using the JAX, which is a Google library for the use for machine learning, because what they give you is an auto differentiation function. But our JAX FEM basically is still a finite element, okay? But the sensitivity, for example, if you try to calculate the stiffness matrix, these particularly Jacobian, you can use the auto differentiation tool. So you explicitly write out the equation and then give you the auto differentiation. And then we can use those sensitivity to do the optimization. So it is open source. It's a Python and has a just-in-time, and also can connect it with the Google, the GPU acceleration. So if you look at the barcode, it's open source. You can download it. And the way, because it can do the sensitivity, give you kind of for free, you can use it for, as I mentioned, topology optimization as well. So the example that you see right here, it's a very typical, kind of compliance optimization, right? What we are optimized here is not just a topology. You see the color bar. The color bar also is going to give you a range of the yield stress difference. So some of the material could be softer, some of the material could be stronger. And so if you co-design this with the geometry, topology, and the material together, you can see the red line, it gives you better compliance. So it's actually about 13% better. And the potential of this is basically you optimize like 3,000 parameters, with the GPU is only 10 minutes. It's relatively easy because it's an elastic problem, And, but the goal is actually JAX-FEM right now. We have already elastic plastic, hyperelastic, all incorporated into this. So we try to do is it really bridge the physics, right, based simulation with the machine learning tools to speed up this numerical simulation. And our application for this is the following. I mentioned about ERC at the beginning, and I'm coming back to here. So at The Ohio State, our PI Glenn Ding, and led his group develop this Agility Forge. Basically, it's a flexible forming operation. And so lots of parts, particularly some larger parts, right? You need larger press. So the idea is you can actually do local heating and different ways and different heating. You can change the tool and you can do basically free, like open die forging, and lots of flexibility. So the question obviously that links to this when you're looking at the deformation path design. Let's say you start with the block and then you want to make this wrench. There are many different ways, go from the top to the original one to this, right? So what you need will be two things. One is globally you want to have the geometry right. And locally, when we look at the material-wise, I also want to get the material property right. And the material property for the metals really depends on your deformation path. So if you can incorporate all these things together, how do we design from the beginning to the end? And many times we have very experienced, engineers or shop floor workers, right? They have very good accumulate 20 years or maybe even 30 years of knowledge, and they can actually plan out this really well. So the question is, can we actually make this as autonomous planning? So one thing really interesting is also a colleague at OSU. They developed this so-called gamification. So it's kind of like a video game. You play with the different paths, right? And say, the goal will be have the minimum number of the hits to get to the geometry that we want. And you can play with this. And then the question is, when you do something like this, you want to get to the mechanics into it, So if you really do a mechanics-based simulation, it becomes very long time. So maybe it takes about even 2 minutes to get one hit, you wait there. Nobody will play this game, right? So this is where the JAX-FEM came in. So the engine of this one is JAX-FEM, and you can put different hitting paths, as you can see, which actually have the physics in there now to give you the geometry as well as the material states. So we put all these things together, which is very nicely. Then what you could do is, now it's only about a few, like 10 seconds, then you have a kit, so people can play the video game. We are trying to actually speed up even further. So the question then next is, I mentioned about this is geometry, but what about the material state? So the material state that we are doing, we build on this JAX-FEM and put the crystal plasticity in. For people here who have been working with the mechanics, crystal plasticity is really nice, but takes very, very long time. So our goal is how do we shorten it, right? So we have this crystal plasticity. We use actually Caradini's, well-established hardening laws to model the slip and twinning behaviors, and we put into the FEM framework, as I mentioned. And then you can actually, calculate, for example, this is just 1D, but we did this with the multi-grams, and we compare it with another open source code, the Moose. It matches pretty well. We also put it as an open source, so you can scan it, you can download it and use it. And the time that we have, it really has a lot of advantage when you have more degrees of freedom. So 5 by 5 by 5, it's probably computational time very similar. But once you go beyond, more and more, you can see the JAX FEM, down is down here, so computational advantage. So with this, then what we can do is we can incorporate with the optimization, as I mentioned. What I really want is the inverse design, right? So let's say, I have the material and I really want to have certain yield stress. And also, I really want to have certain energy absorption capability. So let's say you have the design, this is where the design stress strain curve comes in. So, if you want to have this design, the dotted one, what is the microstructure you need to give you that behavior, right? So you can start with the Euro angle, with the very constant ones across this grid. And each one, if you do the inverse pore figure, material science people would know, it's right here, which is the initial design, it's a red line. So the question is, can we find out the microstructure that will give us this dotted line, which we basically use a JAX CPFEM and put the optimization. And after you run it, it's about 40, different iterations. You can see that each cell at that block is actually going to give you a different phase. So it ends up with this geometry, you look at the microstructure. So now what you can do is, with AM, you can actually can make it locally control the properties, right? And going back to the deformation, I'm just going to finishing up with this last slide. If you want to have this kind of stress strain behaviors, even at different ratios, what is the loading path, right? Remember I talked about this for, the gamification. So what is the loading path can give you these different, say stress strain behaviors, and you do the inverse analysis, and then you can see that you start this one and actually also can calculate the strain path for you. So with that, I'm going to finishing up. And I think, there are lots of opportunities. This is a slide I used 2 years ago. I'm pretty sure next time I come over here, even 5 years down the road, I probably still use this slide because there's so much things you can do. And for all these different knobs. And I would like to, again, thank my students, collaborators, of course, funding agencies for making this happen. So thank you very much. No.
One, yeah, perfect. Thank you very much. That was wonderful. I greatly appreciate you being here and giving this talk. We have time for questions. Who likes to go first?
We always say students first, right?
Yes. I don't, yeah. Otherwise, I can, I know some of the faculty. I will pull them up, right? Yes.
I'd love to reference a previous. Oh, sorry, I'm Eric. I'm a freshman, first-year engineering student, hopefully going into mechanical.
Oh, great.
Thank you. So,
Really student first, you can be, there's no high school students here, right?
all right, I'd love to reference a previous slide titled Differentiable JAX FEM for Co-Design. there's a graphic on the bottom right of what I believe is a yeah, if you wouldn't mind referring back
This
to it.
one?
Keep going back.
You mean, okay, before.
Yes. In
Maybe-
essence, what I believe is a temperature gradient
This one?
of a. Oh no, keep going.
Which direction?
Left, I believe. Back.
No, the differentiable is this one. This one? Yeah, this one. Okay, here we go.
Thank you. Okay, so what I believe here is a gradient here. I'm wondering if you've explored taking advantage of that gradient you see to find different characteristics throughout a part. In essence, if you wanted like more flexibility on one side of a part and less on the other, have you applied your model to analyzing that or making a part with those characteristics?
Yeah, good point. So the question is whether we have made this one in reality, right? No, unfortunately, we haven't made it. But I think it would be interesting if someone, we can try to do that, right? Because one of the things, as you see here, is not taking consideration yet. It's an ideal case, assuming each voxel could be controlled independently, right? But when you do the manufacturing processes, actually that certainly is whether you can do it. So that's the first question. Second, many manufacturing processes also have this tolerance gradients, right? So what we are doing now on another project is actually putting the manufacturing constraints into this optimization. Because right now, each voxel really you can independently control from the optimization point.
Thank you.
So when you're really looking at the code design of the material topology and the process, right? So I mentioned end of the process. So you need that kind of manufacturing constraint put into the optimization code. Yeah, that could be a PhD thesis, so keep working on that.
Okay.
Hello. All right. I'm Nico. I'm also a freshman, and I hopefully go into mechanical engineering. What was the name of the company that was in the video? The
Oh,
beginning
that is a
presentation?
Makino Lab.
Kino Labs.
Yeah, so you can do Makino Labs, search it, you find that.
Okay,
Yeah.
thank you. Because
Yeah.
I just find the industrial robots and integrating that with manufacturing is kind of what I want to go into.
Yeah, so the founder is a really entrepreneur, so many times when you think about this, people will question about the robot's rigidity in something like this forming, So you do need actually a lot of also compensation in the robots to make that work. Yeah, and they located outside of Los Angeles, so yeah, if you're looking for internships,
I mean, I'm on the East Coast.
Oh, East Coast.
It's kind of fun,
Okay.
but thank you.
It's okay, you can travel. Other questions? Yes.
Or you can start up here, right? Yeah.
Hi, I'm Sophie. I'm also a freshman, also hoping to go into mechanical.
Oh, great.
But I was wondering, you mentioned your powder blown machine, I believe, in
Yeah.
your lab. Can you talk a little bit more about how you guys constructed that, or what was the process like?
Oh, the powder blown ones, right? Let me see here. Do I have it? Yeah, so the way, yeah, this one, right? So you're asking how we made this one, right? Yeah, so, well, we use, this is a DED, so we use IPG lasers, and we use Fraunhofer nozzles, and we use Aerotech stage, and actually the environmental chamber was developed by undergrads. So you can see the environmental chamber was developed there. And the photodiode systems, so when you put all these things together, the photodiode system was developed by a PhD student at that time. Actually, Sam was the one. And then you have different hoppers. So we have the hoppers from both GTV as well as Power Motion. And then, so the powders, two of them are here, 4 of them at the back. And then what we do is we develop their own mixing. So the mixing is not the one like foam alloys. They mix them, and then they feed them to the line. This is the mixing during the line. So there are both advantages and disadvantages of doing that. So basically, we have a mix, at the back, and then we feed it in. So you can see that they're coming down, and you use a laser to melt it. And the stage is a 5-axis stage. Yeah.
Okay, there's a question on the end.
I had a question about.
Can you introduce yourself?
Yeah, I'm Vikrant. I'm a 5th-year PhD student
Okay.
in mechanical engineering. And I had a question about accelerating the computational simulations. So like you did with deformation, what do you think about doing it for additive manufacturing? Is the process of simulating additive manufacturing very hard to be accelerated on the GPU? And I see that you can do a lot of things with inverse design if you can capture the physics of laser melt pool manufacturing.
I'm sorry, can you ask the question again? I couldn't hear you very well. Can maybe hold the mic closer?
Yeah. So it was very interesting to see your work on accelerating the deformation simulations. And my question was, did you think about accelerating the additive manufacturing
Oh, yeah.
simulations? And is the process of physics very complicated to capture it in the first place?
Definitely. That's ongoing work, definitely. And we actually, so we first started with this gamma code ourselves. And basically, that's a thermomechanical. And then we did another just thermal. And then we have gamma mechanical, which is thermomechanical. So the topic is very wide, actually, because when you try to simulate the residual stress, so you have the equivalent strand, just put it in layer by layer. So that's another way to speed up that instead of just doing pass-wise. So you can think about a different, certainly there are more research going on also using the AI to speed it up further. So you can think about creating the linkage, local model and connect it to multiple models to do that. There are many research in this area, so I think for that topic, it probably needs another talk. Yeah.
Okay, I think we're going to wrap up the Q&A. Thank you again for being here, for giving a presentation.
We missed a question from faculty.
Yes, we did. Oh, AJ, you wanna have the last word? Okay, go ahead. Of course.
I don't want to disappoint our visitor. So one of the early slides that what you have pointed out, you showed the correlation between the geometry of the 3D printed part and the defects.
Defects, you're talking about the powder bed ones?
Yeah, I believe. They were put in metal
this one.
parts.
The powder bed ones,
Yeah,
right?
exactly,
This
powder
one. This one.
Yep, that's correct. Thank you. So I wonder that if the true interaction between the laser and the powder is at the microscopic scale. There are no dimensions of this part, but I'm guessing they're in millimeters or centimeters. Why the defects should have to do with the geometry? So why the microscopic events correlate to the macroscopic design aspects? Anything in sight?
Yeah. So if you look at this, some of the things are 0.5 millimeters, right? So those are some small ones, and that's just because the size of this, the CT scan has some size limitations, and they want to put different geometries into this. If you look at 0.5 millimeters, and also the laser spot size typically about 50 microns, So it's about 10 times difference, right? And then depends on also how you scan it, There's also turnaround, which is also affect, because if you use the fin, like here, if you scan this way versus scan that way, also different. If you have the ROP, you scan it different way. The boundary condition, that's why the boundary conditions start to show up. And this is where some of the mechanistic feature I talk about, is going to give you an impact on the heat accumulation. And that one will also affect the Melpo stability.
If I just may have a quick follow-up question. So now if I want to take this and create a complex geometry of the heat transfer inside an engine, now how to have the laser path planning and the scanning to take, because if each geometry is going to allow me to have different type of defects,
Right.
how to optimize that for a much more complex geometry is where I'm going actually.
Yes, very good point. So let me just go back to this one, right? So you can see that the scanning pass, you can actually, lots of different combinations you can do, right? And this is why, in some way that we are kind of like this, because it really gives you, the photodiode system we put in has a resolution about 6 micron. So we can actually capture these local, scanning pass effect. So your question is, how do you design the scanning pass, right? For the larger part. So I do think, when you design it, it's another inverse ones. For example, you try to have much more uniform thermal signatures. That could be your optimization, right? And then you can actually use the mechanistic feature also to predict and then close the loop. There might be some other ways, but there could be a lot of research going forward. We haven't done that, but I do think the next step will be also how you design the laser pass to create better, the scanning pass, the profile, yeah.
See, I
But
knew
the
I liked the
method
student
is, I just
answer
wanted-
questions much better.
No, this is great. So but my point is the method that we talk about right here is scalable, because you look at those mechanistic features, it really scalable, you can, if it's a very large part, you can just increase the array size, to do that.
Okay. Thank you very much one more time,
Okay.
please, for a distinguished lecture.
Thank you.